So on the topic of work and energy, the very first concept that we'll be discussing are the types of energy. The very first type is kinetic energy, or the energy of an object in motion. So some real-world examples would be a ball rolling across a table or a soccer player running across a field. On the kinetic energy formula, we have to note that velocity is squared, meaning that kinetic energy will always be positive. Because even if velocity is negative, once it is squared, it will be positive. On top of that, because mass doesn't usually change, any change in kinetic energy relies on velocity. And if velocity is doubled, then the kinetic energy will increase by 4 times because of this square. So the second type of energy, or potential energy, is basically the energy that is stored within an object. Some examples in the real world would be a book sitting on top of a shelf, or a swing at its highest point. One type of potential energy is gravitational, such as the free fall acceleration that this person experiences as they jump off this cliff and directly onto the lake below them. Now the formula for gravitational energy is mass times gravity times height. Now gravity will always be the same unless you're on a different planet, and mass usually does not change. So any change in gravitational energy depends on the height that you are above the ground. And because height is directly proportional to potential energy, if the height above the ground is doubled, then potential energy will also be doubled. The second type of potential energy that we're discussing is elastic. For example, springs or coils or rubber bands. The formula is here, 1/2 kx squared, and an important thing to note is that x is squared, meaning that if the distance that a spring is stretched is doubled, then its elastic potential energy will increase by 4 times. On to the concept of conservation of energy, let's first view a demonstration to get an idea of how it works.
So conservation of energy tells us the energy will research over here, which means it will not escape, or it will transfer to another form of energy. Okay, but the general idea is the energy is transferred from one to the other, and the energy will still be the same. So first of all, I'm gonna swing this red wine bottle and keep this remain still here. Okay, and I'll let you guys to see how this conservation of energy works in this experiment. So I'm gonna swing this. As you can see, this one remains still, and it gains a little bit kinetic energy. And you see that this water bottle, this red wine bottle, actually stays still, and it just transfers back and forward simultaneously. As you can see, this one swings, and this one stands still for a bit, and then this one will steal some of its energy, and it will swing again, and this one remains still.
So what we learned from that video was basically that energy can't be created or destroyed, it only changes from one form to another. So for a real world example, you can see here that there's an apple on a tree. So at first, while it's on the tree, it will only have potential energy due to its height above the ground. However, as it falls down onto the ground, it loses some potential energy, which then turns into kinetic as it gains acceleration while falling to the ground. Now let's look at this example of a pendulum that's swinging back and forth. So assuming that it starts here and we pull it back to its highest point, it will only have potential energy. It will not have any kind of kinetic energy. However, as you let it go and it swings here to position B, it will have both equal potential and kinetic energy. However, as it swings down to its lowest point, it will no longer have any potential energy, but it will have it will reach its max kinetic energy. This is a perfect example of how energy is conserved because as the pendulum's potential energy decreases, its kinetic energy increases, and as its kinetic energy decreases, its potential will increase. And again, this shows that energy cannot be magically created or magically destroyed. It only changes forms from one to another. So when discussing the mechanical energy of systems, we can apply the conservation of energy to the initial and final energy of the system. we know that energy can't be magically created or destroyed. So whatever energy the system it begins with, it must also end with that much, as long as there's no work from outside forces that are being done. So the example I have here is a person holding a ball out from on top of a building as it falls down to the ground. So as the person holds the ball out, there's only gravitational energy working on the ball. So we can label that as mgh. And while it falls, it will continuously lose potential energy. And at this final point, right before it hits the ground, it will only have kinetic energy, which we can label as this. Look at this through these charts. You know that the mechanical energy of this entire system is conserved. So the ball's energy at position A and position B should be equal. At position A, there's only gravitational energy. At position B, we know that there is only kinetic energy. And they should be the same. These equations, we know that mass is not a factor of the transfer of energy that's happening, but we will notice that as the height of the object decreases, the velocity will increase. So work happens whenever energy is transferred over any certain displacement. Some examples from everyday life would be pushing a shopping cart or walking up a flight of stairs. To help understand this better, I will show two demonstrations of work.
In this demonstration, I'm pushing against the wall, but I do no work despite exerting a lot of force because the wall doesn't move any distance. In this demonstration, I am also doing no work because even though I lift the dumbbells up and down, they always return to their original position, which means that there's no displacement and therefore no work.
And the formula for work is force times displacement. And it's important to note that force is mass times acceleration. And displacement and force are also directly proportional to work. So if displacement doubles, then so will the work being done. And if force is doubled, then again, work will also be doubled.